All right, welcome everybody. Let's go over some announcements here. First of all, Thursday is going to be a little bit unusual because of the Winter Technical Conference. I'd encourage everyone to attend. It's not obligatory for you to go to the tech conference, but during the time that we'll normally be in here from 3:20 until 4:15, I was looking at the schedule and I noticed, ironically, it's something that's kind of related to water resources, and so the Mosul Dam emergency grouting. The material for that day's lecture is going to be posted online, and so there will be a lecture you need to watch. That's why I'm not making it required to go to the tech conferences. What you're required to do is watch the lecture that I'm going to be posting. And what I hope you'll do is watch that lecture and also go to the tech conference. All right. The next homework assignment, homework 3, only 2 problems there. And don't let that intimidate you. That doesn't mean that they're really big. It just means that I've broken up the assignments into pieces this semester. And actually, both of those problems are 3 reservoirs types. And we're going to go over the 3 reservoirs concept in class today. So I think after class, you could probably do both of these problems in under an hour if you wanted to. Also on Tuesday of next week, we're going to have our first quiz of the semester. And I haven't written it yet, so I can't tell you what's on it. But I will tell you it's not going to be a Excel problem. I mean, you may want to bring your laptop anyway because you never know when we're going to use Excel, but it won't be on the quiz. All right? Yes? No. I mean, we've only had 5 lectures so far, so it'll be stuff we learned in CE 331 so far. Yeah. You want a formula sheet. So did Ben, so therefore I put a formula sheet together. And be careful what you wish for. All right? Because this is the formula sheet I put together several semesters ago for the final exam. So you don't need to have all these formulas for the test that you're gonna, or the quiz you're gonna have a week from today. But yeah, you don't need to memorize the equations for the quiz. That's not, I mean, the Jane equation in your brain, that would just be taking up space, right? There's better things you can memorize besides the Jane equation. Like the Colebrook equation, that's what you should be memorizing. I mean, come on guys, just roll with the punches. You're getting way too anxious about this 1% quiz.
It can make a difference.
Yes, yes, thank you for the good suggestion. There will be. There will be crazy conversion factors, yes. Just because you asked so nicely. All right. So, now, regarding this Winter Technical Conference, maybe some of you are already aware of the situation at the Mosul Dam. I happened to learn a little bit about it from an article that was in a magazine not more than a month ago. It was talking about, it's kind of a dam with an interesting history. It was built in the early 80s because they wanted kind of like a big national infrastructure project to distract from the fact that Iraq was currently at war with Iran and a lot of people were dying and it was really expensive, and so they built a big dam to sort of, you know, like take the attention elsewhere. And it did a lot of good, you know, irrigation, flood control, electricity generation. It allowed for lots of agriculture that previously hadn't been possible. You can see it looks pretty green in the vicinity of the dam here. I think this photo was probably taken during the winter or the spring because this is what it looks like during the summer. It's a little bit more bleak, scorched earth, but a really long earthen dam that, as the Army Corps of Engineers put it, the site was chosen for reasons other than geologic or engineering merit, which is kind of like the understatement of the century. It was built on a terrible, terrible location where the foundation is soluble. And so the rock that's built on is a really soft limestone that's just eroding. And they have to grout sometimes hundreds of tons per day of cement underneath the dam so that it doesn't just wash downstream. And one of the things that makes this concern especially acute is the fact that for more than a year, the city of Mosul was out of Iraq for more than a year, but the dam, they didn't have control over the dam for a while because it was taken over. And so they've been sort of playing catch up on the maintenance of it, and they have projected that if it broke, which, you know, there's a fair chance that it could, then it would completely submerge the city of Mosul, and the wave of water would eventually even make its way down to Baghdad several days later. And so I don't know if you can see this. The red means that it would be more than 25 meters deep of water. That's a lot of water, 25 meters. Here in the greenish blue is 18 meters, and then the flood delineation basically includes most of the city of Mosul. So it's a really interesting engineering challenge, and the Army Corps of Engineers has been closely involved in the rehabilitation and the emergency engineering work. So I have no idea what Ken is going to talk about on Thursday, but he's an interesting guy and it's an interesting topic, so I'd encourage everybody to make an effort to be there. Okay. Well, let's talk about the 3 reservoir problem. So here's the problem. We have water in 3 reservoirs that are connected at a central junction. And we have an uncertainty about which way the water is flowing and how much flow rate there is. Some of the system is pretty straightforward. For example, A is the reservoir that's the highest. We can be pretty sure that the water is going to be flowing out of that reservoir for obvious reasons. And the same is true of reservoir C. The flow situation in pipe DC is pretty clear cut. Water is going to be flowing into C because it's at the lowest elevation. The ambiguity arises with reservoir B. We don't know if the water is going in or out of that reservoir. Now remember, it doesn't necessarily matter where the elevation of the junction is. That's not going to control where the flow is going in or out of reservoir B. But let's take it to the extreme. Just play a thought experiment. What if the elevation of the water surface at reservoir B was just 1 inch lower than reservoir A? So they're basically at the same height. Well, if you have the elevation of the water surface at B about the same as A, then obviously the water is going to flow out of both of those reservoirs and into C. And the opposite is true, is if we lowered the water surface elevation of reservoir B much, much lower to where it's nearly as low as reservoir C, then water is going to be flowing from A into B and C. But there's a big middle ground there where we're not exactly certain whether the flow is going to be in or out. So what would you guess affects that flow direction? You know, what are the factors that have influence on whether the flow is into the reservoir B or out of the reservoir B? The amount of water in it? Okay, that's going to have an effect on the water surface elevation, which definitely plays a role. The flow rate? What do you mean? Can you elaborate? Okay, out of A. So you're saying if you've got a lot of flow going out of A, then that could affect things, the flow in this pipe, the QBD. You're right. Was there another guess over here? Yeah. I love it. Exactly. So think of what he's saying is, all right, so what if pipe DC is so small, the water's not really going to want to go through a small pipe, just because there's a lot of resistance to flow in a small diameter pipe. But what if the pipe to DB was a big diameter pipe, so that there's less resistance? So the water would go into both reservoirs, but it's going to find the preferential path, and it's going to immediately balance the flow rates depending on the resistance. And so the factors that affect resistance are the roughness of the pipe, the diameter of the pipe, and when we're calculating the F value, the velocity affects the roughness of the material F. So what we're going to be doing in some hand calculations I'll show you, and then in some Excel calculations we're going to work through together, is trying to solve this problem of what direction is the water flowing, what's the head loss through each of the pipes, and what's the pressure at the junction. All right, so think about the options that water has. Water is going to flow out of the high reservoir into the low reservoir, but the middle one is what's indeterminate. And the flow rate, how quickly the water is flowing through any of these pipes, depends on the head loss through the pipe. And by head loss, what we mean is there's a certain amount of energy at A. And the total energy of the water in tank A is just simply equal to its elevation. There's no velocity head and there's no pressure head for the water at the surface of tank A. And the same is true, the water at the surface of tank C, just the energy is its elevation. And so the water is traveling from A to C. There's an energy change. There's a loss there. The head loss, H sub F, is just equal to how much energy is lost as it takes this pathway through the pipes. So that's what we mean by H sub F, is the energy loss. And we know, because the elevations are given, we know how much energy loss there is. And you can think of the energy loss as it's like the spending money you've got for flow rate. The more head loss you have to spend, the faster the flow rate is going to be through the pipes. But if these two tanks are about the same elevation, then the flow rate is going to be quite meager if the elevations are about the same. It's the head loss, the elevation difference, that drives the flow from one point to another. The trick here, though, is we don't know exactly what the velocity is. And so we can't calculate how much head loss there is unless we know the velocity. And F depends on the Reynolds number, which depends on the velocity. So this is going to be another one of those circumstances where we have to make a guess and iterate, fix our guess, iterate again, and so on, in order to find out what's the flow rate through the pipes. So strangely, the H sub F, the left-hand side of this equation, we know because of the given elevations of the water. But what we don't know in this formula, in the Darcy-Weisbach formula, in the three reservoirs problem, we don't know velocity or F. So that's one equation, two unknowns, which normally gets us in a tough spot. But we'll start with a guess and improve on that guess through the iteration. And what we're looking for in convergence is something we know has to be true, is that at junction D, continuity has to be honored. And by continuity, I remember, what I mean is that in equals out. You know, that simple idea that was the bulk of Chapter 5 last semester in fluid mechanics, that flow into the junction has to equal the flow out of the junction. So here, we know that QAD is flow in, and flow out is QDC. Flow is coming out of the junction from there. And then depending on the first guess we make, our first guess may say that there's no flow rate in BD. And so if that was the case, we'd be looking for the flow rate in and the flow rate out to be equal. And so we're going to calculate, we're going to solve for velocity in Darcy-Weisbach equation and then find the corresponding flow rate and see, does flow in equal flow out? Is that honored? Because if it's not, then that tells us that we have to change our guesses in a certain direction. We either have to raise or lower our initial guess of how much energy there is at D. And that's one of our starting guesses, is we have to make an estimate of the total head that's available at D. Okay, so lots of uncertainty here. Yes? Well, there's lots of situations where pipe networks have pressure coming from more than one source. You know, there can be a network that's being pressurized both from a water tank and from a pump. And so you're trying to find out what the flow rate through a pipe is going to be when energy is being added at two different locations. And that's what this is we have energy at A and B that's contributing to the flow through DC. So anytime you have more than just a simple single pipe segment, if you've got branches in pipe networks or flow rate coming out at different locations or coming in at different locations, then these sorts of ideas will start to apply where you've got uncertainty that requires guesswork. Great question. All right, so here's the solution method. There's a step-by-step 1, 2, 3, 4 thing that we have to go through. But first I want to introduce you to the governing equations here. The first thing that we're going to always keep in our minds is the definition of head, which is just another way of measuring energy, but with units of meters or feet. And so particularly it's going to be the head at D that's important for us to either calculate or estimate, the head at D. And the head at D is going to consist of 3 different components, because at D it's an enclosed pipe where there will be pressure, it's got some elevation above a datum, and the water is going to be flowing, so there will be a velocity head. So there will be 3 components to the head at location D. Now at the reservoirs though, the head is just equal to the elevation, because it's open to the atmosphere, which means that at the surface there's no special pressure, and we assume the tanks are large enough that the velocity isn't really fast up or down. That's a pretty good assumption. So that's one of the governing equations, is just what we mean by head or energy. And then the other is we're going to be using the Darcy-Weisbach equation to solve for the velocity. Head at D is calculated by looking at the losses between points. So at A, there's a certain amount of energy at A, and the head at D is going to be less. There's less energy at D because water was flowing through this pipe and energy was lost due to pipe friction. So this first expression here, head at D, is head at A minus HF. I hope that makes sense, because it's just saying the direction of flow is important in knowing whether the energy is going to be higher or lower at a certain point. And so the energy at D is lower than the energy at A because of the losses. Now consider this other one. We also could calculate the head at D from a different direction. We could say the head at D is however much head there was at C, but then this time there's a plus. Why is that positive sign there instead of the negative sign which we saw in the last equation? Okay, so he said you're spending the energy going to C, you're losing energy as you go in the direction of flow. Now the opposite is true here. If you're going against the flow, that must mean there's more energy. So there's more energy at D than there is at C. That's why the water's flowing. The water always goes from high energy towards low energy. And so there's some driving force that's pushing the water in this direction. So that means there's more head at D than there was at C. So this is a governing equation. These 2 different equations here allow us to calculate how much energy there is at D based on a starting point and losses, either in the direction of flow or against the direction of flow. And then I guess those aren't losses, those are gains in energy. Any questions so far? Okay. So here's what we're going to do, step by step. We're going to begin with a guess of the head at D. And our text suggests that sometimes what you can do is just assume that the head at D is equal to the elevation of the water in the middle tank. But it turns out that you don't have to do that. You could choose any elevation between C and A, and eventually the solution will converge. But if you want it to converge faster, an easy thing to do is just assume that the total head at D is equal to the actual water surface elevation at B. Okay, next we're going to find equations for head loss in terms of F and V. So we're going to rearrange the Darcy-Weisbach equation and find out how much head loss we have in each of the pipes based on this guess. It's a little quieter today, right? It's not all the way there, but I'll get a pool noodle. That'd probably cushion the impact a little bit better. All right, so steps 3 and 4, we're going to have to assume some F value and then find out for an assumed F value what would be the velocity. So just if you're keeping track, we're already 2 assumptions deep into this. We assumed a head for D, and now we're assuming an F value.
Okay, so the odds of all 3 tanks in the real world being the same size, like let's say tank C is its diameter is half the size of A and B.
Mm-hmm.
That means there's less mass of water in the tank, so it wouldn't be able to balance those pressures out, so the water would just eventually.
I'm glad that you asked that question. That's an important question. And it turns out that the diameter doesn't have an effect because even if a tank is wide or narrow, down at a certain elevation, the pressure is the same because the delta P is equal to delta H times gamma, which is the unit weight. So the diameter would affect how quickly the water level is rising or falling, but it's not going to change the energy situation. The energy situation only depends on the water surface elevation or, like what depth into the tank we are. Yes? Only that you would have to calculate your head differently. If it was an enclosed tank and you were given the pressure in the head space is some pressure, 250 kPa, for instance, then you'd calculate your head at A equal to its elevation plus its pressure head if it was enclosed. So we can handle that. We just need to know what's the pressure in the head space if it's not open.
In other words, the both tanks have to be the same height.
That's right. Yeah, the tanks can have any diameter and any height, and we'll be able to solve this problem. Yeah. That's a good question. So what if there's a fixed number of moles of gas in there? If the water level went down, then the pressure would decrease. I mean, if we had some problem like this where we were saying there's a fixed pressure, then maybe there's also a compressor that's keeping it at the pressure that we like. But I don't know. It would just depend on the way the problem is written. Yeah. All right. So our problem-solving procedure here is that we have to guess how much energy there is at D as a first guess, and then we have to guess how rough the pipes are in order to proceed. And once we've done that, we can calculate the velocity based on our guess of the F value. And once we have some guess velocity, we can calculate the Reynolds number based on that, and we can get an updated version of the F value. You could go to a Moody diagram, but you can't automate a Moody diagram in the same way that if you type in the Jane equation in Excel, then it'll automatically calculate a new F value for you when you have your new velocity and you want to calculate an updated F value. Once we have some new updated velocity, still using this formula, the rearranged Darcy-Weisbach equation, we'll calculate the flow rate just using Q equals VA. We'll check to make sure that flow into the junction equals flow out. And then the rest of this procedure, you don't need to memorize the procedure. So don't sweat that. But do sweat this. Understand the criteria. The if-then statement that I have here, it is really important to understand that if-then statement. So if the flow out is more than the flow in, then that means your guess of how much energy there was at D is too high. And think of it this way. Now you're going to be assuming how much energy there is at D, or like how much pressure there is at D. If you made a guess that's too high, then that's going to be forcing more water through pipe DC than there really should be. So it'll be out of balance. So if your guess was too high, then that means there's a lot of flow out of that pipe. And the flip side of that is that if your flow out of the junction is less than the flow in, then that means you need to raise your guess of HD. Unfortunately, this iterative process doesn't tell us by how much it should be changed. We have to not just guess at random. We can do a little bit better than that with Solver, but we can't knock this thing down to like a single iteration. We have to do 2 or 3 iterations to get everything to converge the way we like. But this is a decision point that is really important, and sometimes, when I get questions on this assignment, the number one question comes because people forget to switch from traditional units to SI units. That's the one I've gotten more than any other, is, G is either 9.81 or 32.2. But then the other question I have is people not quite understanding how to know whether to raise or lower your next guess. So I'll emphasize that when we get to that point on the spreadsheet to try and help you see why we need to either raise the guess or lower our guess. What we really like is to see that flow is balanced, and that tells us that we're done, as long as the F values are also stabilized. All right, so here's the example we're going to work today. And I put that Excel file onto MU Online. So what you should do, if you haven't already, is go into MU Online, and here on the home page is a folder that's called Selected Excel Files from Class. Download that to your desktop or wherever you're going to be able to find it. See if we can all crash MU Online. Get in the same file at once. All right. Yours is the student version because the instructor version has the answer, and I don't want you to see the answer. Not yet. Yes?
What property would be in equilibrium with the water changes by during flow? I want you to Q in, Q out, and say like equilibrium.
Yeah. What that means is that the head D is the same whether you calculate it from the direction of the lower elevation, the lower reservoir going towards D, or from the upper reservoir going towards D. So like the equilibrium is that no matter what direction you calculate the energy at D, it comes out the same. And that's a good question. That's like the implication of flow in equals flow out. It just means that all of the energy works out, that there's no contradictions in how much energy there is at D. Because we're going to have to change our guess of how much head there is at D, and let's say our first guess was that it was equal to 110, and so there's no flow in or out of reservoir A. But when we lower the head at D, then that's going to tell us what direction. If we lower it, then that would mean the water's going from A towards the junction. If we have to raise the head at D, then that tells us it's going into tank A. Great questions. You guys are really thinking today. All right, so here's our starting point. Oh, you know what? I jumped the gun. I want to show you these hand calculations first, just so you can appreciate how nice Excel is going to be for this one. I'm not going to actually make you do the hand calculations, but I wanted to show you what it looks like when you do this manually. So we start with some guess of how much head there is at junction D. And you'll see that the guess I chose was, I said let's have the energy at D be equal to the water surface elevation at A. And so I said 110 feet. And then I'm trying to calculate how much head loss there is in pipe BD, and so I used this governing equation to say that the expected head loss would be 10 feet. And so does that make sense? If we've got 120 here and it's 110 at junction D, then that means there's 10 feet of losses as the water flows through that pipe. And we do a similar thing with the other pipes as well. There's no losses through pipe AD because the water isn't flowing. But through pipe DC, there is 40 feet of losses, meaning that the water's flowing from D towards C, and if the head here was 110, that means we're losing 40 feet of head over the course of that flow. All right, the cast iron pipes, here's the K sub S value, and for galvanized iron, calculated the cross-sectional areas for those. And then I put it into the Darcy-Weisbach equation because I want to find out what is the velocity but I still don't know an F value either. So I'm just going to guess an F value, and like somewhere midpoint on the Moody diagram, like if you look at the range of values on a Moody diagram, at the lowest end of the spectrum it's 0.008. At the highest here, highest typical values, we'd usually only see maybe 0.04. So I'm here in the middle. I just said, let's assume as a starting point 0.02. And so here is that 0.02. And then we can get some guess velocities based on that assumption. And if we've got guess velocities, then we get Reynolds numbers from those. And with the Reynolds numbers and the relative roughness, we can have an updated guess of the F value. I can get that either from a Moody diagram or from the Jane equation. So now I've got an updated F, I can get an updated velocity, and now here in step 7 is where I start to prepare for the flow balance analysis. I say, all right, well, if it were those velocities, what would be the flow rate through each pipe? And then I compare the in versus the out. Now my first guess here was that the elevation of the head was 110 at the junction. And that guess turns out to be too high. And the way I know it's too high is because the flow out of the junction is bigger than the flow into the junction. And why can't that happen? Why can't we have more flow out than flow in? Because it has to equal. There's nowhere else for it to come from. If there's zero flow in pipe AD, then the flow through BD and DC have to be equal to each other. But based on that guess, that cascade of guesses that I made, then it turns out HD is too high. So I just randomly picked some new elevation. I said, let's lower it by half a foot. So I would do the whole thing over again with a guess value of 109.5 feet. Okay, yes? Excuse me? Is the A and B mixed? Yeah, there was no flow through this pipe. Yeah, because my first guess was that the head at D is equal to 110. And so if the head there is 110, then there's no driving force for the water to go from the tank towards the junction, because the total energy in the tank is 110 and the total energy at junction D is 110. So that's maybe another one of the reasons why in our first set of iterations we assume that the head at D is equal to the elevation in this tank, just because one of the pipes has no flow in the first iteration. No, I don't think so. Conceivably, something like that maybe could happen depending on the diameter of pipe CD, but like if there's negative pressures in the pipe anywhere, then we're still going to be able to, that won't make our results invalid. Like we could do a drawing of the hydraulic grade line, and even if the hydraulic grade line is below the physical elevation of the pipe, then the energy solution is still going to be valid. Okay, so we've gone through this paper set of calculations just so you could get a feel for how the steps translate into a problem-solving process. And I designed this spreadsheet to be a similar thing, where each of the steps here is numbered that we're going to be going through. And if you've got access to the notes, you can refresh your memory on what each of the steps are and what we need to do. All right, so here we have each of the lines identified, and we need to put in some information here. We need to have the epsilon, which is the equivalent sand roughness. I'm calling it here K sub S. It's the same thing. For cast iron in feet, the value is 0.00085, and that comes from a table in the book. And again, we have cast iron for pipe BD as well, so 0.00085. Galvanized iron is a little bit different. That is 0.00050. Okay. The lengths we can get from the drawing. Pipe AD, you should enter in a length of 750 feet for that. The length for BD is 1,000 feet and 500 feet for pipe DC. The nice thing is, of course, with Excel, we're only going to have to type a lot of this in one time, and then when we copy and paste our iterations, all that drudgery will be behind us. All right, it needs the diameter here in feet, and it's given in inches, so be mindful of that. The diameter of AD is going to be 8/12 of a foot. The diameter for pipe BD is going to be 12/12, so 1 foot diameter. And then the other one is also 8/12. Okay. We can calculate the cross-sectional area. We all know that formula by now. Pi times d squared divided by 4. Okay. And we can apply the formula down. Can you see any of those numbers from the back? Is it just too small? You got to bring your binoculars if you're going to sit on the back row. All right. So our guess value of the head at D. Let's do that same 110 feet that was in the paper calculations. So let's say 110 feet, and then I'm going to have it just look up here at my first value rather than typing that in. Okay, so 110 feet. Now the head loss through the pipe. This is where we have to think a little bit and look at the drawing here. Okay, so the pipe we're talking about is AD. So AD, the calculation I should do for that is going to be 110 minus our guess value. So there's no head loss through pipe AD if the head at D is 110. Okay, now what about BD? Okay, so from B towards D, it's going to be 120 minus the guess value of HD. And then to get the head loss through this pipe, we're going to say it's 110 minus 70, because we know that 70 is the elevation of the destination. So there's 40 feet of head loss there. And all those should be positive values, because by loss, we're sort of saying that we don't need a negative value to indicate that it's a loss. By definition, all the values there should be positive. Our initial guess, we don't really have any basis other than let's just pick something in the middle and hope that that means it'll iterate quickly. It converge faster than if we had a bad guess for that. All right, now velocity here, I'm going to use the Darcy-Weisbach equation, which I've rearranged to solve for in terms of velocity. So put in the square root of h sub f times diameter times 2 times g. And for this, we need to be careful. It's 32.2 because it's traditional units. Okay, so that's in the numerator, and then in the denominator divided by f, which is I-27. I can't click on the cell location anymore because it's centered, and the formula is starting to get in the way of where my value actually was. And so I just typed in I-27 to refer to where that is. And then divided by L, so the length of the pipe. I did the divided by 2 times just to avoid having to put in any parentheses. So we type enter, and then it says the velocity through that pipe is 0. That doesn't mean there's a mistake. That's true. It should be that, because based on how much energy we assumed at D, there isn't yet any flow through that pipe. But through the other pipes, hopefully, fingers crossed, we get some flow rates here. Yeah, that's right. Both of those velocities, that's what the velocity would be if there was this much head loss and if there was, this was the F value. We can calculate a Reynolds number from that. The kinematic viscosity of water in terms of British gravitational units. Here's the kinematic viscosity of water. That's 1.138 times 10 to the minus fifth. So I'm going to do, for kinematic viscosity, the velocity times the diameter divided by the kinematic viscosity, which is, what did I say, 1.138 times 10 to the minus 5. No Reynolds number because we have no velocity. But those pipes that do have flow have a corresponding Reynolds number. And now we're going to use the Jane equation to give us a new and improved calculation of the F value. Here's the Jane equation. Let me drag that down so it's easier to see as we key it in. All right, so 1.325 divided by the logarithm of the relative K sub S divided by 3.7 divided by D plus 5.74 divided by the Reynolds number, which is K27 to the 0.9 power, and then I square it. Yeah. The area? Mm-hmm. Diameter squared by 4. Not sure. Just try doing it like pi, so times d, so E27 squared divided by 4. No, oh, it's maybe the pi function is screwed up or something. I'm not sure. I have to come back to that. Okay, let's see. It's the kinematic viscosity. Yeah, it's 1.1 times, let's see, here's the value of kinematic viscosity. You've got it there somewhere. Let me write it on the board. I've got it up there. I'm not getting by there. So the new F value you should get, let me execute that. That's not good. We'll just stick with our original guess here of 0.02 for the one that has no flow rate, because if you have no Reynolds number, then you're going to be dividing by 0 here. So we don't yet have a good guess for that. All right. So then the new velocity, we're going to just use this formula again, but based on the new F value, square root of H sub F times D times 2 times G divided by F, where the F we're talking about is the new one, L27. Thank you. Divided by F divided by L. Okay. So there's not going to be any flow through that pipe still. But we now have a different guess of the velocity through the other pipes. And now we have to here just qualitatively say, is it going into the junction or out of the junction? So from BD, the flow is going into the junction, and DC, water is coming out of the junction there. And the reason why I have you put that in that cell is just so that when you calculate the error, it's obvious what's the inflow and what's the outflow. Okay, so this flow rate we're going to get just from the velocity times the area. All right. And then here in the field for error, let's calculate the outflow minus the inflow. Okay, I'm going to pause the recording so I can circulate around and see how your calculations are going. Okay, so let's interpret these results. The criteria that I said was that if out is more than in, that means your guess of HD is too high. In other words, we're trying to just guess how much energy there is at D. And if we give it a lot of energy, we're going to be forcing water through that lower pipe so that there's more flow through the lower pipe than the upper pipe. But if we were too low on our estimate, it would be the opposite way. So I'm going to type in just a text here, conclusion. I'm going to type in out is greater than in. Guess of HD was too high. So we need to lower our guess of HD for the next iteration. All right. So here we are. I'm going to copy and paste all of this information just with Control-C, Control-V, and so now I don't have to calculate the areas again or anything like that. But I'm going to have a new guess of HD. How much lower should I go? It's really a crapshoot, that second iteration. So I'm just going to say 109.5 and then see how things go based on that. All right, so the head loss through the pipe, I should be able to copy and paste, and we'll just to make sure that it makes sense. Okay, so what we're saying is there's half a meter of loss of head from A to D. So this was at 110, and if this is at 109.5, then yeah, there's going to be half a foot of loss. And then 10.5 feet of energy loss. Because it was at 120, and we're saying the total energy at D is 109.5. So yeah, these H sub F values make sense. Now our guess, we can do better than just randomly assuming 0.02 this time around for all of them. I'm going to use my old guesses, so I'm just going to say equals and click here on the previous iteration so that it picks up these updated F values. At least two of the three are updated. Pipe AD didn't have any flow yet, so that's just still our initial guess. I can copy and paste in the Darcy-Weisbach calculations of velocity. I can copy and paste my calculations of Reynolds number. And it's so nice, with two keystrokes, I can save all those paper calculations of finding my Reynolds number over again. All right, so we've got a better Reynolds number. That means now I can get a better value for Jane equation. I just pasted the middle one because I'm going to drag it up, and then I'm also going to drag it down so that now it's doing the Jane equation for all three of those rows. Because if I had just done a copy paste straight across, then it wouldn't have that updated one for here. So I'm going to drag it from the lower cell. You know, you can drag down, but you don't always think you could actually drag up too, but you can. Velocity, copy and paste that. Flow direction. Now, I can't just copy and paste that. That was some mental work that I was doing on my own. So if the head is at 109.5 at the junction, then that means the water is flowing from B towards D, from A towards D, and then from D towards C. So that means that it's coming in from A, in from B, and out towards C. All right. All right, so this is an inflow. The flow rate is V times A. Oh, I want to use the updated V. So the velocity times the area for all of those. All right, and now the out minus the in. So we have one out minus both of the ins. So there is a negative value there. So what that means is in is greater than out. So our guess of HD was too low. So this is like Goldilocks, right? Well, 110 was too high, 109.5 was too low, somewhere in the middle will be just right. Okay? So what we need to do for the next iteration, raise our guess of HD. By how much? Well, we don't want to go all the way to 110. So somewhere in between. Any questions before we start iteration 3? It seemed like there, in a handful of cases, there were slight differences in velocities or F values, and I don't know if those are maybe in the way that your computer is estimating pi, or if you typed in 3.14 instead of the pi function. But for small, like less than 1% differences that may arise at this point, I'm not too concerned yet. It's when we get to the final iteration, the flow rates and the F values, hopefully will tighten up and match my spreadsheet versus yours. All right, so I'm going to live dangerous here. I'm going to copy all of it, all at once, instead of doing it column by column. Just copy everything, Control-C, Control-V, but I'm going to change, once I do that, I'm going to change this one to say 109.75. Okay, and then I'm going to do the calculation of in minus out. Actually, rather, I'm going to do out minus in. All right, we could do a goal seek at this point, right? What if analysis? So data, what if analysis, goal seek. Our goal is we want to have it change this guess value of HD until the error is 0. And just to let you know, that's part of the reason why for these other ones I have them as references to the cell above rather than typing in the number over and over again, is because I want everything to change based on this one cell, which was a guess value of HD. I want to make sure also that I'm using the updated F values. It looks like it is. Question in the back? That's a good question. And I'll show you here in iteration 3 why you couldn't have done it in iteration 2 and why it's not enough to do it in iteration 3, why we're going to have a 4th iteration even with goal seek. That's a good question, because you may be thinking maybe I could have done it earlier, but it turns out that you can't, because we're trying to get there's two convergence criteria. One is that the F values are constant within the step, and the other is that the flow is balanced. And with goal seek, we're only having control over the flow balance part of it. So we'll have to have sort of another copy and paste iteration even after this goal seek. All right, so what if analysis, goal seek, and I'm going to try and get this, some of the errors to 0 by changing the head at D. I let it run wild. All right, it found something here. 109.88, that's a pretty good value. The flow rates equal each other, so the flow rate out is basically 4.7, and I have the sum of these together is 4.7. If you highlight 2 cells, then down here at the bottom of the screen, it will give you some statistics here. So that's a quick way of adding them together. 4.7 basically is the flow rate. But it's not good enough, not for us, because we're perfectionists. And look, the F value hasn't converged all the way. So this flow balance is only true if these were the F values. But these aren't exactly the F values. We can do better. So we're going to do one more iteration to make sure that the F values are within 2% and that the flow rate is completely converged. And why not? I mean, if all we have to do is copy, Control-C, and paste, Control-V, then the F values are stabilizing. And I'm going to do the goal seek one more time here. What if analysis, goal seek, I want the sum of the errors to be 0 by changing this guess value. And we'll change it ever so slightly, or not at all, I guess. It was already converged enough in the mind of goal seek. Maybe I'd have to turn on solver to get a tighter iteration, but the point is that if you do a % error, then the difference between the F values here, I could just do a quick % error here, equals the difference between the F values divided by the updated F value times 100. So there was a 9% change within that iteration just for the pipe AD. But when I go down into the fourth iteration, it's less than 1% difference in the F value within the iteration. So here are the flow rates. They don't look much different from this step, but it is helpful for us to have an actual good estimation of what the roughness coefficient is, F. So now we're converged. We know the answer. The question was, what is the flow rate through each pipe? Now we can answer that we know how much the flow rate through each pipe is. Here's the flow rates. Through pipe DC, the flow rate is 4.699 cubic feet per second, etc. All right. One last thing we need to do, part 2 of this problem is asking what's the pressure at the junction. And what you'll remember is that in the problem statement, we were given the physical elevation of that junction. We know that the physical elevation of this junction is 85 feet above the datum. And now, through that whole iteration process, we know the total energy at D. So now what we're going to say is how much of that total energy is pressure. And that's what the second half of the spreadsheet allows us to do here is we're going to rearrange the definition of head because we know that the head is 109.88, etc. So I'm going to have this reference up to the total head, and then the elevation at D is 85 feet. The velocity head's a little tricky because this is a junction of 3 different pipes. And so you could say, what's the velocity head in pipe BD? Or you could say, what's the velocity head in pipe AD? So let's find the velocity head in all 3 pipes and then average them and say that that's the velocity head at D. That's probably overthinking it because velocity head is usually a small fraction of the overall energy. But since we're in Excel, we can sort of afford to overthink it. It's not so bad to iterate these things manually. So velocity head is just the velocity in AD. So it was, here's our velocity, squared divided by 2g. Remember, g is 32.2. Oh, thank you for catching that. I got a little overzealous with my divided by. All right, so I'm going to drag that down. So I have my 3 velocity heads, my average velocity head. And so the pressure at D now, I'll substitute this formula to calculate the pressure at D. It's going to be the total head, all the energy minus the elevation, minus the velocity head, average, multiplied by gamma. And for water in traditional units, we'll use 62.4 pounds of force per cubic foot. So then that tells us the pressure in pounds per square foot. And if I want that in PSI, I just divide by 144. So now we know how much pressure there is at D. All right, and now you know how to solve the homework that's due next Tuesday. Or at least you've seen it. You may not know yet, but I hope that you should save your work because the spreadsheet will be useful for solving the homework assignment. Although it would really be, it would be a sign of commitment if you started like from scratch. If you made your own spreadsheet rather than just modifying the one I gave you, like think of it your own way. All right? Let's look at some announcements here before we finish up. All right, so tomorrow morning, I'm going to post the solution to the assignment you submitted today. So homework 2, which you uploaded to MU Online, I'll post the key to that tomorrow morning. I'll also grade your assignment, and then I'll post the link for our lecture recording, which, we're having that recording for Thursday's class. And I hope to see you all there to hear about the Mosul Dam. All right, have a good one, and I will see you next Tuesday.